Okay, guys, so now we are going to move on to the next topic, which is the anomalous property. Now, as you can see, it is written over there that it is being shown by the first element of every group. Now, what can probably cause this? So, first we have to understand this, that we are talking about this anomalous property not only for this group, not only for group 13. I'm talking about the anomalous property of group 13, 14, 15, 16, 17, even in 18, right? In all these groups, we get to see this anomalous property happening. Now, what is causing the, who are showing it? The first element only. Now, don't get me wrong here. It doesn't mean the other elements cannot show anomaly. They can. They are going to be called as exceptions. But here, these anomalous properties are being shown by the first element for the same reason. That's why, guys, we call it not an exception. It's an anomalous property. Now, here we see the main reasons which are common in all the group elements. First element, it's size. Now you might say, sir, because of small size, what can probably cause it? So let me explain this to you now. If I'm talking about an atom has a very, very small size, so it would have exceptionally high ionization energy. It would have exceptionally high ionization energy. If it has exceptionally high ionization energy, then we can definitely, connect it with the inertness of the inertness of the element. So the element starts showing themselves like they are inert. That is what we see in the first element of every single. Example group 13, boron. It shows characteristic like inert people. I'm gonna give you an example while I'll be teaching you the chemical properties there. For every single element in the group 13, if you want to make a hydride out of it, means let's say I'm talking about aluminum. You want to make an aluminum hydride, or you gotta make a gallium hydride, it is comparatively easier to just react it with hydrogen. But when we are talking about boron like hydrides, we can only get it formed by this lithium aluminum hydride treatment. And guys, you know that lithium aluminum hydride is a strong reducing agent. That's all we need, all we know every single time. Need we every single time. So now that is one of the ways. Now, second thing we can talk about the electronegativity, guys. They work hand in hand, right? If they have high ionization energy, the basic reason behind that was because they were exposed to the nuclear charge. Now they have high electronegativity because of the same reason. And now you might say, sir, what would that cause? Because, guys, you can clearly understand if you have a high electronegativity, then definitely the bonds are going to be much more polar. The bonds are going to be much more weaker than the others, right? So that is the electronegativities is what can I call. And there is another thing about electronegativity, guys. High electronegativity can affect a lot of things in physical properties. For example, if you notice in group 16, group 17, and group 15, nitrogen, oxygen, and fluorine is what I'm talking about right now. They are the first element of the groups, correct? Group 15. I'm just talking about a generalized version, guys, because it's the same thing I'm gonna see in every single group, and I'm gonna just tell you that okay, you can refer to that video at that time. So group 15, group 16, and group 17. You know the first element of all these three groups are nitrogen, oxygen, and fluorine. These three people, because of their exceptionally high electronegativity, they can form hydrogen bonding. Correct? That is how it is anomalous. That is not being shown by phosphorus, right? That is not being shown by sulfur. That is not being shown by chlorine. Only by these people. In DNF block, guys, you have learned it or you are going to learn it that block elements, they can get high oxidation state. They can achieve a huge oxidation state with these people only, those who have high electronegativity. So these are like not electronegativity, although it sounds a very small topic, but guys, it has a huge variety of application if I look into the chemistry set field. So that is another thing. Now, if I talk about absence of d orbital, this is probably one of the most important things. While going forward, guys, I'm gonna refer to many of the PYQs, and there absence of d orbital is being asked in different ways. But this topic always comes up. Now, what is the reason? Like, what would happen because of this? Although I'm gonna explain this in a very detailed manner right beneath it. So, due to absence of d orbital, what actually happen is you cannot expand your valency. Guys, there are many people who have multiple valencies, correct? Like phosphorus, if I say phosphorus has valency of 3, it also has a valency of 5. Now how is it happening? Because guys, what happens is that phosphorus's electrons, they have a d orbital, so they can extend their valences. But can it be done by nitrogen? No, no. Nitrogen's highest valency is 3. So like technically covalency is 3. If I talk about the rest of the valencies, it can go to 4. Nitrogen can go to 4. Okay. So technically it is 3 highest valency. So now, how is that getting formed then? So nitrogen doesn't really have a d orbital, correct? 2s2p. So it cannot expand its valency, but everybody else can expand their valence. For example, if I have to stick to this chapter, guys, boron cannot have valency more than 3. Boron cannot have valency more than 3. But if I talk about aluminum, who is right beneath it, because of its d orbital, because they have a d shell, vacant, but it is having, right? Because aluminum is 3s2, 3p1, then if it is 3, then 3d has to be there. As a result, guys, aluminum can extend its valency all the way to almost twice of boron, which is 6. Okay, now these are the things that we are going to talk about. Okay, and how they can go to +6 oxidation state, which way are they using the d orbital and stuff. That is something that is going to be discussed. But right now, guys, let's talk about the effect of these problems first. Okay, as you can see, that is what we have started taking into consideration. That is the covalence up to 4. See, because of these three topics, what all anomaly are visible, are experienced by us. As you can see, the first thing is the covalency up to 4. So you can have the highest covalency of 4. Okay, in the group, not the highest, I shouldn't be saying highest, but it can go up to 4, which borons or any other people cannot go. Like, I'm going to give you an example of this. Okay, I'm going to reframe my words in a minute. First of all, guys, let's talk about boron. It has only 3s and 3p orbitals, correct? It has only 3s and 3p orbitals. So if I talk about boron over here, like, boron has electronic configuration with including only 2s and 2p orbitals. So it is going to be 2s to 2p1, correct? It doesn't really have a d orbital. So if I have to draw the electronic configuration, I'll be drawing in this way, right? Now, right now, what is the valency of boron? If I talk about covalency, it is 1. Now, in the excited state, we can take boron to the valency of 3. And this is what happens, guys. You get the valency of boron as 3. But for boron, you can see there is again a vacant orbital present in it. So it can utilize that vacant valency orbital, and it can go up to valency of 4. Boron can do that. Okay. Like an example, if I talk about BCl3, similar thing happens with aluminium as well, okay? Because they have similar electronic configuration. So these are actually known as Lewis acid. As you know, AlCl3 is a very, very famous Lewis acid that you have learned in Friedel-Crafts alkylation or any kind of aromatic nucleophile electrophilic substitution which has been using AlCl3 there, right, as a Lewis acid. So that is the same reason, because it has a vacant orbital. So that's why aluminium and all these group elements, they can increase their covalency. And for boron, it can go up to 4. So boron's highest is 4. Let's say I'm giving an example. A boron getting valency 4. Let's say I have BCl3 coordinate covalent bonded with ammonia. So there'll be a minus charge, plus charge. If I look into this compound right now, guys, so boron has 3 bonds with chlorine, 1 bond with nitrogen. So overall covalency is going all the way up to 4, not more than that, right? But for aluminium, because of the presence of d orbital, right, what would happen is for aluminium, because of the presence of d orbital, 3s2, 3p1, this is 3d. You know what this aluminiums can do? They can accommodate coordinate covalent bonding in these vacant orbitals, using these vacant orbitals as well. As a result, guys, aluminium shows compounds where its valency goes all the way up to 6. So you can see that it can accommodate up to 6 valence. It can go up to 6 valency because of the presence of d orbital. So this is one of the anomalous property that I was talking about from the very beginning. Now, this is something, but where do we see it? Is it only aluminium and boron? The answer is no. It is for everybody when it is second member. So only the first member can stick to the orbitals which are available for it. Like for boron, like I said, its covalency can go up to 4. Okay. But for aluminium onwards, the covalency can increase from for 6, sometimes beyond 6 as well, right? Because of the presence of the orbit. And that is something we see not only for aluminium, for everybody other than the first element. Okay, and again, not only for group 13, for every single group, everybody other than the first element can extend their valencies to a very high value, but not the first element. It cannot do that. Another example in group 15, I'm going to teach you. Let's say for group 14, if I talk about, there also you have carbon. Carbon's highest valency you can take it to is 4, because carbon is 2s2, 2p2, right? Like this. Then excited state, all the orbitals are taken up. So carbon cannot even extend their valency ever beyond 4. But when you go to silicon and people like that, again you have the d orbital getting generated there for 3 subshell. As a result, guys, you get to see more than 4 valencies. You get to see 6 valencies in silicon systems also. It's like silicon, germanium, and all the people. So this is the main gist of this absence of the orbital. We're going to see much more questions of this topic. All right, like see, that is what I'm going to talk about right after this. Like you can see the point over here. Carbon forms only tetrahalide. That means carbon cannot go beyond valency 4, CCl4, right? But other can make hexahalide like SiCl6, GeCl6. All right, there is this is what we can see for group 14 elements, right? Again, there is a thing, guys, which I'm trying not to disclose right now, because if you have been watching this video from the beginning, you know that there's another place where we are going to see some anomalous property getting generated. You can give it a guess, and we are going to see that whether your guess is right or not. Try to think, guys. Other than the first element of these groups, group 13, group 14, group 15, specifically these three groups, other than the first element, which other element can show some anomalous property like the first element? It is like them, but which element can do that, right? This is a thing that we are going to get to know in the end of the session. But right now, guys, put your bets on the table, right? Now, we talk about the reactivity towards nucleophile. Let's cover this point up as well. Now, guys, you know that they are Lewis acid. Group 13 people are Lewis acid. Not group 14 people, though. Group 13 people, they're all Lewis acids. So group 13 people themselves are electrophiles, that means. Because what are the electrophiles? Those who need electrons, right? And the electrophiles, when they combine with somebody, that is has to be nucleophile. So if I talk about BF3, BCl3, all of them, the very beginning, I have told you that they have a vacant p orbital, right? As they have a vacant p orbital, if there is a nucleophile, like let's say ammonia or any kind of nucleophile, somebody who has a lot of electrons, they can make bonding with them, right? In the vacant p orbital. What is this orbital? Vacant p. Vacant p orbital, right? So these people can do that, right? But the point is, guys, for BF3, this orbital is not entirely vacant. What happens is, guys, there is a important thing that we should be which should be talking about here. That is the concept of back bonding. What is this concept of back bonding? This is saying that if you have an element with a lot of electron and you have an element with a place to accommodate electron right beside it, and if both of them are from the second group, Guys, this is a very important thing. If both of them are from the second group, then what happens is, then they can show concept of backbonding. Means fluorine can donate its lone pair to the boron which is there, which would result a partial double bond character in this position. Not only this fluorine, guys, this can be done by all the three fluorines out there. So as a result, this pure p orbital is not really that much vacant like the BCl3 molecule. The BF3 molecule vacant orbital is somewhat taken. So if I talk about nucleophilicity, like electrophilicity, if I talk about Lewis acidity, same thing, then BF3's Lewis acidity is definitely going to be lower than BCl3. Okay, because of the absence of the vacant orbital in BF3. Guys, again, don't say that it is not there. The absence, the vacancy is not there. That's not the right term to say. Because if you open up the chapter equilibrium, there, guys, in the very beginning, they have utilized this concept. They haven't really disclosed this concept yet, but they have used the BF3 molecule, have shown that how BF3 molecule can bond with ammonia with a coordinate covalent bonding using this vacant p orbital. That means, guys, they do it. It's not like they never do it. Yeah, but the rate would be lesser. That would be definitely low. But they can act like a Lewis acid. BF3 can also act like a Lewis acid, but it's a weaker Lewis acid than BCl3. This is my point. That is there. So I believe this much is clear to all of us. Now moving on to the next one, this is the forming tendency to form the multiple bond. This part is not directed to the group 13 and group 14, guys. This is directed to the entire group chemistry. Okay, what are kinds of multiple bonds are present actually in this group chemistry? There are two types of multiple bonds. One is p pi p pi. Okay, the other one is actually there are three types of p pi p pi, p pi d pi, and d pi d pi. Okay, let me tell you about about these three types of bonding real quick. When we are saying p pi multiple bond, that means what we try to say is, let's say atom A and atom B, both of them are using their p orbital in order to make the double bond character. So if you can understand what is the p pi d pi, what does that mean? So one of them would be using their p orbital, the other one would be using their d orbital. And what is d pi bonding? Both of them are going to be using the d orbital for the bonding purposes. Alright. So these are the three types of bonding which are there. As you know, guys, that only parallel bonding can make double bonds. So that's why we have to know that they are parallel to each other. Now, if I talk about an example of p pi bonding, then you can understand, guys, if I talk about the formation of oxygen molecule. This pi bonding, it is made up of the 2p orbital of both the oxygens. So that's why it is a p pi. If I take a p by d pi bonding, then, guys, we can take an example of SO2. In SO2, in between the sulfur and the oxygen, the bonding that gets formed, here we use the d orbital of sulfur and we use the p orbital of oxygen. So this can be called as a p pi d pi or d pi p pi, same thing. Okay. And d pi, when both of them are having d orbital, with that they are making the bonding. So these are the three types of pi bonding which are out there. Okay, as you can see, I have drawn two pictures as well. I have taken two pictures. Here, if you see, in the p pi, what am I showing you? That here the d orbital of sulfur and the p orbital of oxygen, they are combining together to make the double bond character. So this pi bond is made up of this pi bond. This pi bond is made up of only electrons, only the overlapping and stuff like that. So that is one of them is making happening by from the p orbital, and the other one is happening with the d orbital. And here in oxygen, you can see the p pi. This is all about the pi. Okay. Now with this general knowledge of all the overall group chemistry, now we can start in a chapter-wise manner. So yeah, you have been doing the generalized information so far. Now, when we be starting the chapters with this kind of mentality, then, guys, now you'll be able to see the topics are very, very, very simple now to you. Let's talk about the electronic configuration. This is something, guys, I guess you already know. It is going to be NH2 NP1 for group 13 elements. If I'm talking about boron family only, so group 13 element NH2 NP1 is the electronic configuration. For boron, if it is 2s2 2p1, for aluminium it is 3s2 3p1. For gallium it is 4s2 4p1, like that we do it. Okay, we just increase it by one shells. The atomic radii, this is a very important thing over here, guys, where the contraction and stuff are gonna get introduced now. So guys, in the very first part of this video, we have discussed about what is called this inert pair effect, correct? We have also talked about what is the D contraction, what is the net contraction, right? These are the things that we have talked about already. Now, because of that, you already know that the thallium in the group 13, the thallium element, it is experiencing both the D and F contraction, right? Thallium is experiencing both D and F contraction. Now, that is what indium is also experiencing in a way. But indium is only experiencing D contraction. Gallium is also expecting D contraction. Boron and aluminum are not experiencing anything as such, because gallium is in the same period with the D block elements actually. Scandium to zinc, after that the gallium. So that's why this is where the D block elements are. This is where the D block elements are. Okay, so that is what the gallium is doing. Now we talk about boron and aluminium, right? What happens when you go for the radius? So guys, the boron radius is the highest. I mean, sorry, is the lowest by vector sense. It's the lowest. There is no issue with that. But aluminium should be the very next, because I'm going down the group. Then gallium. Then thallium. This is what the electronic configurations are for atomic radius of group 13. That is how it is supposed to be. But guys, this gallium comes before aluminium in reality. So boron, gallium, aluminium, indium, thallium. Boron size suddenly gets smaller than aluminium because of the D contraction, guys. So here, because of D contraction, gallium size has been found to be even lower than aluminium. Okay, because till aluminium there was nothing, no decontraction or anything so far. From gallium onwards, the decontraction gets generated, and it is hitting the gallium so much that it is getting even lower than the aluminium size. This is one thing for the radius atomic. Let's talk about ionization enthalpy now. Guys, you already know what is ionization enthalpy, but I would still like to ask you a few questions right now. Okay, if I say, let's say, the ionization enthalpy of an element has been found to be negative. First of all, tell me, guys, what do you understand by it? Okay, you pause the video first, because I want you to pay full attention over here. Pause the video, just understand what do I mean by that, and then see whether it is matching with my answer or not. So there is an element whose ionization enthalpy has been found to be negative. What does that mean? Right, that's the question. So I believe you have tried this question now. So I'm going to tell you what is the answer to this question. The answer to this question is that what you understand from it is the examiner knows nothing. That is all you understand from here. Because if an examiner is asking you the ionization enthalpy of an element has been found to be negative, that means, guys, it is impossible to have. Because ionization enthalpy can never go negative. It is always a positive quantity, correct? Irrespective of anything. Now, because you're taking out electrons from a body, guys, right? So it is always going to be asking for energy to take this out. So ionization enthalpy is the only parameter which is always going to be positive, always endothermic. Now, what am I writing here? The first ionization enthalpy of group 13 elements are more than corresponding alkaline earth metal, which were expected. Metals are always going to have a low ionization enthalpy because they're metals. They want to release electrons, correct? But when we talk about the non-metals, group 13 elements means, guys, yes, boron, aluminium, fine. But gallium, indium, thallium, they are more like in the characteristics of the metals, metalloids or metal, right? Specifically metals, we can say. So now, if I talk about these people, ionization enthalpy would definitely be more. So that is not even a point of discussion. But what is the point of discussion is, if I talk about ionization enthalpy, what is your expectation from the, definitely, you know, guys, if I talk about group 13 from boron to aluminium to gallium, indium, let's say this is what we have. Now, more we go down the group, the size is increasing. So ionization enthalpy would be decreasing. Ionization enthalpy would be decreasing. More you go down the group. Like that, we can judge this idea. Now, as a result, we are expecting boron to have the highest ionization enthalpy. Then who? Then aluminium. Then who? Then gallium. Then indium. Then thallium. This is our expected order, right? Now look at the values for a second. What do you see? Boron is the highest. That's no problem with it. But the second highest is thallium. Original order is boron after the thallium. Then who's next? Gallium. Then aluminium. Then indium. This is the original. Now, what is the cause behind it? Why is thallium coming all the way up here? Definitely, guys, D plus F contraction. Definitely D plus F contraction. Why is gallium over here standing? Because of D contraction. Right? Because of that, it is there. So that is why, guys, the order goes like boron, thallium, gallium, aluminium, indium, based on the formula, based on the values that you can see. And you can see, guys, I'm giving further informations to you. After boron value, you can clearly see thallium is next, then this, then this, then gallium, then aluminium. Then indium is on the bottom side, okay? Write it down now quickly. Okay, all done. Make sure, guys, you learn this chapter in graphical method. In graphical manner, when you learn a chapter, the chapter would make much more sense to you. Let's go for electronegativity. Now, guys, in electronegativity order also, you kind of have an expected order, which you know that more you go down the group, your size is increasing. So electronegativity is supposed to be decreasing. Right? Now you check the answer that they have given here. 2 is the highest for, that is understandable. Then after that, who's the very next electronegative element? That is thallium. Who next? Then we have indium. Boron, thallium, indium. Okay, boron, thallium, indium. Then you can see gallium, then you can see aluminum. Now, guys, you must ask me a question. That's a boron, thallium, gallium, this much is fine. Why is indium coming over here? Because you just told us that why is thallium taking that jump all the way up to the second spot, then why gallium is there. You told us all those things. But why is indium coming up now in terms of electronegativity? But not, it wasn't there when we were discussing about the ionization enthalpy. Why suddenly here? Now, all I want you to understand over here is, guys, we are talking about electronegativity. Electronegativity is the tendency to attract electron, correct? Electron attraction is based on two properties, not one. It's not only about attracting electrons. It is based on two properties. What are the two properties? What are the two parameters which is involved in the electronic attraction? Pause this video for a second. You try to interact, you try to answer something, whatever you understand from there. Only then you'll be able to get the benefit of these classes. Okay, I believe you have tried it now. Now you listen to this very carefully. It is consisting of two properties. One is definitely the Z star, definitely the attraction power for which we are actually talking about. But guys, there is inter-electron repulsion over there as well. You do not take the electrons in. You don't take the electrons in, right? But you are dragging the electrons towards yourself. So now, guys, you have to always understand whenever we are talking about any property of electronegativity, electron affinity, we are talking about density of electron. We're dealing with the density of electron. So definitely there, the size would also have an effect, right? If you have a high attractive power, then that's a good thing. But guys, if you have a small size, then these parameters are also gonna face the interelectronic repulsion and stuff like that. That is why indium is coming. So there would always be a thing about chemistry, guys, that you need to know the facts first. Then you can explain that, right? Here, first and foremost, guys, in inorganic chemistry, there are so many exceptional things happening. So you need to keep your facts straight. You need to keep a blank page right now with you. You need to keep on writing down these, what do we call this order, these trends in there, because trends are there in JEE, in both in JEE mains and in JEE Advanced. So JEE mains, it is that 100% is there, right? Now, going to the next one, which is the oxidation state. If you see, what am I writing over here? For group 13 elements, we can definitely expect the valencies are going to be 3, 14 going to be 4. So you can here see written that this is 333, no problem in that. In indium, it is showing both 3 and 1, and the main part is in thallium, it doesn't show 3 that much. It shows only +1 valency. Now this one valency is caused by inert pair effect. If you don't know what is inert pair effect, guys, watch the first 15 minutes of this video. First 20 minutes of this video. You'll be able to understand what is inert pair. Okay. Now, due to inert pair effect, what would happen is thallium would show +1 valency, correct? Similarly, if I talk about the carbon, silicon, germanium, tin, lead. If I talk about carbon group, you can see the valency is 4. Whereas for lead, the valency has been found to be 2. Because of the same thing, inert pair effect. Now, there are so many questions that is coming from here, I'm going to ask you a simple question right now from this topic. You try to answer this question if you feel like you know about this chapter. Guys, TL's valency is 1, but I can see compound goes by the formula of TLI3. How is this possible? Okay, while I'll be teaching it forward, you try to think about these small things. Acha, in the very beginning, not the very beginning, in middle somewhere, I told you that other than the first element of a group, there is another kind of element, those who can show anomalous property. And I asked you to guess for it. And that is what we are talking about right now, guys. The last element of that group, of group 13, 14, and 15, they show also anomalous property. I hope you got it correct. So they show anomalous property because of the inert pair effect only. I believe this much we are clear. Now, TL can form TLI3. What can possibly be the reason? Think about it, guys, and write down the answer in the comment section of this video. Now, here I'm going to continue with this with a JEE Advanced question, which is GaCl2. It does exist, but how is it possible? How can gallium has a +2 oxidation state? That doesn't add up, right? So here, what actually happens is in GaCl2, you get Ga connected with. So it's actually, let me break it down to you. Okay, in that way, I think it would be easier. GaCl2 Ga is +2 valency. That is not possible. For them, you have to have a +3 valency or +1 valency for gallium. So as a result, what happens is gallium dimerizes. Ga2Cl. Okay. Now I'm going to tell you the real story. This Ga2Cl4 structure is GaCl4. This is plus, this is minus. If you see right now, gallium is showing +1 valency over here. Here it is showing +3 valencies. Okay, here it is +1, here it is +3. So guys, it is nothing. It's not +2 actually. It is actually in the form of GaCl4. So as a result, it is nothing but coexisting with both the +1 and +3 there. Okay, so this is the question that they ask in JEE Advanced, not in this straightforward manner. There was some sort of complexity in that, but you need to know this particular basics in order to solve the question. Okay. Now let's talk about the chemical properties of boron. Now, when we talk about that, guys, I think I told you already that it is going to show some anomalous properties. Like you can see that boron can never make B3 plus because it can never donate all the 3 electrons out there. Cannot do that. Now, why would it not be able to do that? Because of its high ionization energy. Why does it have a high ionization energy, guys? Think about it a little bit. Because of that small size. The high ionization energy, it can never form B3 plus. That's why, guys, boron always make covalent compound. It always wishes to make covalent compounds. But for aluminium, it can make both ionic and covalent compounds. It can make both ionic and covalent, right? This is the chemical reactivity of BX3. And like I told you guys, we are going to talk about this, that BX3 is so unreactive. Formation of B3 plus, so definitely difficult. But BX3, like boron compounds, are also almost unreactive people. All right, because of their like, what should I say, stability, or should I say lack of formation of ionic character, or should I say that high ionization enthalpy. Whoever you want to blame it, you can blame it, but make sure they are all circling up to the same place. Okay, that is that. Now, these are the question-based approach, as you can see, from different competitive examination, and I have tried to give the answer to all these kind of questions. Through that, I am going to complete the rest of the chapter for you. Okay. Now let's come to this question. So let's start with the first question first. Okay. And you'll be able to see every single question that we've discussed right now. It is in a way that you know about the concepts that we have gone through. It is coming from there only. The first question is, except thallium, all the other elements are trivalent species. But the trivalent species have 6 electrons that they can accommodate in there. What I mean from this question is, see, for an example, for a reason that thallium cannot go all the way up to the valency of 3, correct? It can go at the most valency that it can go to is the valency of 1, correct? Because of inert pair effect. Now, still we get to see there is an element out there called TLI3. Now, how is it possible? The basic way, why is it in there? It's actually, this molecule doesn't break into TL plus, TL3 plus, and 3I minus. It's not how it is actually in reality. In reality, TLI3 breaks into TL plus I3 minus. TL plus I3 minus. So here also the thallium is not plus 3, it is plus 1 only. So I3 minus is the anion, not 3I. So that's why it happens. Guys, now you pause the video. I believe right now we are in a time, we are in the moment where we should be able to solve the questions from chemical bonding, right? So right now, just pause the video and figure out what is the configuration. I should rather say what is the hybridization or geometry. Specifically, you tell me what's the shape of I3 minus, right? So just pause the video and write the answer in the comment section. I'm going to give you the answer in the end of this video. What is the shape of I3 minus and what is the hybridization of I3 minus? It's a very important question. Now, moving on to the next question here. The Lewis acidity trend of boron starts from BCl3. See, guys, what I'm trying to do over here, let me clear that out to you. These are all PYQs, either from JEE Mains or from JEE Advanced, or a question which I have taken, which is needed to solve a PYQ. Okay, so that's why some of them are questions, some of them are statements, right? This is a statement I want you to know. What is the statement? The Lewis acidity trend of boron starts from BCl3, not BF3, starting from BCl3. So this is something I just told you guys, that BF3 shows the concept of back bonding, correct? So as a result, we don't consider this to be a Lewis acid, that strong of a Lewis acid. So from BCl3 onwards, we consider that the Lewis acidity is higher in there. Okay, so BCl3 would be the highest, then BBr3, then Bi3. This is the Lewis acidity trend, correct? Now BF3, if I talk about it, definitely it doesn't show that much of Lewis acidity at all. The next thing over here, guys, AlCl3 achieves stability via dimerization. Guys, you know that these group 13 elements, they are all electronically deficient species, And why is that, guys? We have just discussed about it. They are all Lewis acids, right? They don't have 6 electrons out there. If I just don't tell you, if I talk about AlCl3, acha, before we even solve this question, okay, tell me whether what kind of compound is AlCl3? Is it an ionic compound or is it a covalent compound? Pause this video and then answer the question. Think about it a little bit. AlCl3, is it an ionic compound or is it a covalent compound? What's okay? Now let me answer the question here. Guys, AlCl3 is a covalent compound. All of you might have thought that it is an ionic compound, but actually it is a covalent compound. And yes, those who got it correct now, it is because of Fajans rule. Because, guys, aluminium has +3 valency oxidation state. It is having a high, what do we call it? Polarizing power. Okay, because of high polarizing power, AlCl3 acts like a covalent compound, not an ionic compound. So, as a result, the AlCl3 compound is being formed by sharing of electrons like this. Now, if it is so, then how many electrons do I have around aluminium? We have total 6 electrons. If I have 6 electrons around aluminium, then, guys, you can understand that it is electronically deficient. I should rather say incomplete octet species. Incomplete octet species, correct? This is what this AlCl3 is all about. So, in order to fill its octet, AlCl3 undergoes dimerization. So, this is how it is gonna look like. Here, now there is a coordinate covalent bond here, and there is another coordinate covalent bond here. That is adding up to 8 electrons. So AlCl3 is always being found in the form of Al2Cl6. This is about it. Now, coming to the next question here, trichloride of boron on hydrolysis gives MOH whole 4. I should rather say POH whole 4 minus Pc. But aluminium from AlH2O whole 6 3 plus. You already know the reason, isn't it, guys? Still try to answer the question here. Why does it happen? Because, yes, because boron has 2s2 2p2 electronic configuration. It has in the excited state, this is how it looks like. So there is one more vacant orbital. So that's why if you are bonding with boron, you can go up to 4 valency that you can see in here. But for aluminium, we have the d orbital, right? The anomalous property. We have the d orbital, vacant d orbital, where they can accumulate more and more water particles. As a result, guys, aluminium can go all the way to 6, right? So this is something. All right. Now, guys, we are going to go to this reactivity towards acids and the bases. Now, I told you this in the very beginning when we are talking about those anomalous property, that boron being smaller in size, it is very, very unreactive. It is kind of inert in nature. As you can see right now, boron doesn't react with the acids and the bases. See, doesn't react means naturally. If you say, sir, I have created a acid mixture, which is like aqua or something like that, would boron not react with it? Guys, that question doesn't make any sense. Because see, we human beings have process to figure out every single thing out there. There can be acids, can be bases where the boron can react with. There are super acids and stuff, whatnot, right? So I'm not saying that it is not reacting with any acids or bases, but natural ones, like H2SO4, HCl, HNO3, the inorganic acids, they don't react with it. But that is because of the small size and the high ionization energy that we know about, right? Aluminium dissolves in both HCl and NaOH. What does that tell you, guys? This is telling you the amphoteric character of aluminium. You know this, that aluminium oxides are amphoteric in nature, correct? Now, you know boron, where boron over there, boron to aluminium, then gallium, indium, thallium, whenever we are moving downwards, you can understand that, guys, their reactivity is increasing a little bit, right? More than boron. If I talk about aluminium, guys, you know, when you react it with HCl, it can react with HCl and it can form AlCl3 and hydrogen, yes? But when you react this aluminium guy with any bases, then it can form NaAlO2 plus hydrogen gas. Very, very special reaction. What is the name of this compound, guys? Sodium aluminate. Where did we learn this first? In grade 10th, remember? But that time it was Al2O3. You did the same reaction with Al2O3. Here it is. Now, aluminium can form NaAlO2. Okay, and that is what making aluminium an amphoteric compound in nature, in small element in nature. NaAlO2, now it also is written sometimes in this way. Okay, they're the same thing, guys. Okay, NaAlOH whole 4 and NaAlO2, because I have not written it, but NaAlO2 is associated with two molecules of water as a water of crystallization. I have not written it, but it's there. Okay, now coming to the next one, white fumes appear around the bottle of anhydrous aluminium chloride. Why? Simple, guys. What happens is when you have anhydrous aluminium chloride, that means you do not have water in it. And when you react that thing, if keep in a bottle, what happens is it reacts with the water in the air. Okay, and from there it forms that HCl and AlOH whole thrice. Just 1 second. So HCl3. So actually, what happens over here is, guys, here now this compound undergoes a reorganization. First, it forms the this hydroxide, and then it further undergoes reaction to form the oxides. So I'm gonna write the oxides directly. If you write the hydroxide, then you write AlOH whole thrice. That thing, okay, or Al2O3. AlOH whole thrice. Okay, if you want to write the hydroxide, but that gets reorganized to an oxide in presence of a little bit of brightest of heat. But anyways, guys, that's not the big deal. HCl is, this is why we get to see that white fumes around. Okay, this question is super duper important for us. Boron cannot form BF3, whereas BF6 3 minus, whereas everybody else can form it. Now, like aluminium can form AlF6 3 minus. What can possibly be the reason behind it? Again, guys, it's something we already know, the absence of deionide. I guess you can see now, because we had the preliminary idea about this, all these concepts all together in the beginning of the video, all the questions, they are nothing but the application of those ideas only, right? So that's why they are the same thing. Now, guys, anyway, coming back to the important species, important compounds of these group 13. Okay, about the important compound, those who are applying for JEE means, guys, you need to know all the kind of trends which are there till physical property and anomalous property of the element. So where I taught you the anomalous property of the first element, that is where you should stop. After that, nothing else is needed for you, right? But still, guys, whenever you see a trend is being discussed, remember that in the JEE syllabus, they mentioned that the trends are there, right? So make sure that you go through all the trends to be on the safer side. Now let's talk about borax. Borax is a very, very important species of group 13, which is something which goes by the formula of Na2 before O7. Okay, that is how I remember it, right? There are O7 and before that there is Na2. So Na2 before O7, right? Dot 10H2. It's a hydrated crystal, guys, no doubt about it. Now, this borax is something, we used to do a test called borax bead test. It's an identification test. You guys might be doing those tests, right? That is called a dry test tube heating test, or platinum wire test in order to identify crystals. Similarly, borax bead was similar kind of a test as well. Now they're saying borax dissolves in water to give alkaline solution. Guys, borax is an alkaline compound. I guess that you can understand by seeing sodium is present. So, guys, our common sense is saying that if I dissolve it in water, we are definitely going to get NaOH out of it, right? That is what we see when borax is further being dissolved in water. We get NaOH, and yeah, this guy, boric acid. See, I'm going to tell you a small story about boric acid. Remember, guys, it's a shortcut and tell. irrespective of any compound or boron. If you hydrolyze it, you get this guy as a product. Any compound of boron on hydrolysis would give you boric acid. Every one of them. Okay. So heating of borax. So that was about the dissolution of borax. So it's a basic salt. Now, heating of borax, guys, you know that borax has 10 water molecules associated with it. So definitely, in the first time, whenever you are giving some heat on it, you'll be able to see this water of crystallization, which is physically bonded with my crystal, is gonna go away. We are gonna get anhydrous borax. We are gonna get the anhydrous salt of it. Then in the very next point, what is happening is if I keep heating this compound, then guys, we get metaborate and boric anhydride. Sodium metaborate. And what is this guy? This is boric anhydride. You know, how do we get this boric anhydride, guys? If you keep on heating boric acid, you'd get boric anhydride. If we need to take out water from there, we can put boric anhydride. I'm gonna come to that part. But sodium metaborate, you might say, sir, is there any shortcut to remember this? I'm not gonna give you a shortcut. I'm gonna give you a real thing in front of you right now, guys. This is something that I do when there is something which is coming out from nowhere and you do not have a connecting link about it, like for boric metaborate thing, and there's a boric anhydride. I want you to gather more information about it. So yes, we used to do a identification test called borax bit test. What happens in that borax bit test, guys? We take this borax, we first heat it. We make this metaborate thing. In reality, I'm going to show you in this video. We make this metaborate thing. Then that metaborate, what we do is we put it in our unknown salt, which you do in practicals. We put it in the unknown salt. And the moment we do that, and then we heat it, it would change color. You know which metal gives the best test of borax bit with metaborate? It is copper. Copper identification is always done by borax bit test, because in that way copper shows a like just a blue color, which is really really beautiful. I'm going to show you this. Just watch this video with me. So first, I'm gonna speak instead of the video. Okay, so I'm gonna. It is already on mute. So borax is test of cobalt. Okay, cobalt also gives brilliant blue color. Not only copper, cobalt also blue or green, depending on what kind of metaborate you're from. Yeah, this thing that you see, this transparent thing, this is your metaborate, sodium metaborate. You know how do they get that? If they just take that borax, borax is a powder. Think about the powder which we apply on our skin, right? Think about that powder. We take this platinum. This is platinum wire, the exact the same platinum wire that you use for Flames test. This is that platinum wire. We take that platinum wire. We make a loop on the top. Okay, make a loop on the top, and then we take some borax powder salt and we heat it in that Bunsen burner. Now see what is it doing? He's taking this. Now this is your metaborate. You have just heated it so much. So first you got anhydrated borax, and then you kept on heating. You got NaBO2 right now. That NaBO2, and you can see in this in the beginning in here in the spatula. You see that here there is a salt of cobalt. Achha, by the way, you see the texture of metaborate walls. It's a transparent, it's like a water droplet, transparent water droplet, but it is solid. It's not like liquid. It is a solid thing. Although it feels like it's a liquid on the top, they keep on heating it. So if you get the chance, to sneak, yeah, if you can look into it, this is just a transparent bead, right? But it is not water. It looks like water, but it's a crystal. It's a solid crystal. They keep on heating it just to get the metaborate structure properly. Then what they do is, for which elements? Cobalt, nickel, manganese, see, chromium, copper also we use this. See what they're going to do it. They're going to use one of the example, one of the unknown salt. Okay, I'm gonna skip it to a little bit far away. So what they're going to do is they're going to take the salt in there, they're going to touch it against the borax bead, and they again keep on hitting it. All right. Let me show you. They're taking too much time just to make the bead. I don't know, maybe they have already given the salt in it. So you just have to touch the salt in it. Okay, that's all. Let's just watch it for a second, okay? Okay, they have already touched the salt in it. But guys, now here's the part. Do you see the blue color right now if I pause it? It's still transparent. It's still very, very not visible. But guys, there's a slightest of blue color in this bead. If you can notice, very light blue color, right? This one. This is one. Oh, this is the cobalt identification test. Now you can see very well, isn't it? This blue color. It's a transparent blue color, like a blue crystal. Okay, it's a brilliant thing. So this is the test, guys, that we do. You know what? With the salt right now, the blue color salt, that is cobalt metabolite. So NaBO, this is your NaBO2, no? So metabolite of transition metals are colorful. If you see that because of the electronic transition that we get to see in there. So cobalt from cobalt metabolite CaBO2 whole twice. That is the color that you see, blue coloration. So this is the part of this metabolite thing, and with that you get boric anhydride as well. Now we're going to talk about this orthoboric acid now. About orthoboric acid, just give me a second whether my audio was fine or not. It was fine on log. Great. If I talk about orthoboric acid, guys, what is the trick about it? Like I told you, in this chapter, now there are two important compounds, orthoboric acid and that borax thing. Orthoboric acid is the acidic form, like borax is the basic salt, right? Orthoboric acid is the acidic form of the boron compounds. So if you take the borax molecule, if you heat it in presence of a little slightest of HCl, you get BOH whole thrice. This BOH whole thrice is having a reorganization to H3PO3. BOH whole thrice and H3PO3 are the same thing, guys. So that's just the way of writing it. Now, just the way I told you, H3BO3 is a hydrolysis product of most of the compounds. You can see that is what I'm showing here. H3BO3 look like this. It looks like exactly like H3PO3, same kind of thing. But now you can clearly understand, guys, that these H3BO3 molecules are capable of making hydrogen bonding, right? From all these points, from all these sites out there. And that's why they end up making these kind of a structure. If I have to point out, guys, so let me show you here. Let's work with this red color H3BO3 molecule, shall we? Now here, you can see that these are the hydrogen bond. This is hydrogen bond, this is hydrogen bond, this is the hydrogen bond, this is another hydrogen bond, this is another hydrogen bond, right? So they're capable of making hydrogen bonds, and they always be in that kind of form, right, with the hydrogen bond structure. Okay, so this is your H3PO3 molecule. Now, a very, very important question that is always being asked. Boric acid is a weak monobasic acid. Very, very surprising fact. Because people would have thought that if H3PO3 can be formed as 3H plus and PO3 3 minus, why not H3BO3 breaking down into 3H plus and BO3 3 minus? Guys, here the acidity is a little different. Let's say this is my compound BOH whole thrice. What is acidity? When you dissolve something in water, that is acidity. Now I already told you that this has a vacant p orbital. So water breaks into H plus and OH minus. Now here this OH minus forms a nucleophilic attack on this BOH whole thrice, making it a BOH whole 4 minus. You have seen this compound before as well. On hydrolysis, we get this. Now with that you get an H plus. That is why it's the monobasic acid. When you dissolve it in water, the catch over here is, guys, this H plus is not a hydrogen of this H3BO3 molecule, right? It is a hydrogen of water. So it takes out the OH minus from H3BO3 and it creates that H plus out. That is why it's a monobasic acid, right? This is a very, very important, very interesting fact as well, isn't it? Now, our boric anhydride, like I told you guys, I'm going to talk about it, how to form it. As you see, that what we do is first we take out boric acid, we heat it. When you heat it, guys, you need to take out water. If you take out water from here, so 2 hydrogen 1 oxygen, HbO2 is what you're going to get. Now again, when you heat it, you need to take out water, but that doesn't add up. How HbO2, if I take out water, how is it becoming B2O3? I'm going to show you this, guys. First, now, in order to understand that, you multiplied by 2, means you dimerize this compound. Otherwise, you won't be able to take out water because it has only one hydrogen. So how would you take out water? You dimerize it. So H2B2O4. Yeah, now you take out water. See, B2O3 is going to be formed. This is a shortcut manner of understanding things, guys. Okay. So this is the thing. Now, why boric acid is considered as a weak acid? As we have seen that, guys, it is a monobasic acid. Same question has been asked in a different manner. It's a monobasic acid, and always show this equation whenever they give this question. Okay, BOH whole thrice plus water breaks down into BOH whole 4 minus plus H plus. Now, why is it a weak acid? Because, guys, it is based on the dissociation of water. Water itself is a weak substance, right? So as a result, the dissociation of water is always less. So the OH minus and the H plus forms are always less. So the H plus released after dissolution of BOH whole thrice is definitely not that high. That's why it's a weak acid. Okay, end it. Now, guys, let's talk about diborane, the last topic, the last compound of this chapter. If you see in this chapter, there is a lot of topic to discuss, right? Mainly, guys, this video is getting so long because of the concepts that we have been discussing from the beginning. But otherwise, you'll be able to see this chapter has no such things in it. It's like straightforward chapter. Diborane is a compound, guys, which goes by the formula B2H6. B2H6 is something that you have heard about, guys, in the alcohol phenol ether chapter in the hydroboration oxidation, right? Same thing, B2H6. B2H6 is a dimer of BH3 at that time I used to tell you. Now, what happens? How do you form this BH3? Remember, in the beginning of this video, I told you boron, like during the anomalous property, that boron hydrides cannot be found like the with the other elements. You just react it with hydrogen and you get it. For boron hydrides, you have to start with a boron halide. It can be anything, okay, BX3. With that lithium aluminium hydride, you understand, guys, the strongest reducing agent is what you need in order to form the diamond compound. Now, in industries, they use sodium hydride, same thing as metal hydride. I need an H minus, which is strong enough to make an attack in there, remove the fluorine atoms in there, right? That is how you get the BH3 molecule. They never write BH3 in any of the places, always write B2H6, right? Now, B2H6 catches fire immediately, spontaneously on exposure with air. What actually happens is you get boric anhydride and the hydrogen gas out of it. I mean the water out of it. This boric anhydride is actually inflammable. Okay, that is why it can catch fire very easily, right? Boranes are readily hydrolyzed to give boric acid. This I guess I have already told you. Not only borane, any compounds of boron, guys, on hydrolysis, you would always get boric acid out, H3BO3, always, right? So this is already discussed. Diborane can form as a to act as a Lewis acid in presence of NMe3 or Lewis. So you know that, guys, B2H6 is a Lewis acid, but in the BH3 form because of the same reason of P or P orbital which is there. NMe3, it is just a way of asking question. It could have been NH3 as well. Same thing, same outcome. This thing. Same thing happened with water reaction as well, right? Isn't it? Which minus attacked in the same way, right? It can attack like a Lewis acid and it can act like a Lewis base. Okay, that's that. You can see that, guys. If you know the topics, it's all gonna be adding up to the same concept all the time, right? Now, inorganic benzene or borazine, super duper important point. When this diborane molecule of ours is being reacted with ammonia, we get B3N3H6, which looks exactly like benzene. This is called inorganic benzene. Okay, this inorganic benzene, it has similar property, but it is more reactive than benzene. This is more reactive. than benzene. This is an organic benzene, more reactive than our normal benzene. Why is it more reactive? Because guys, every single bond over here is polar, and I guess you know that when if somebody is polar, it is always going to be more reactive, like that. Now, guys, to end this video up with the last topic, B2H6. B2H6 formula is something that we have talked about, and the bonding also. In BH3 mode, we have learned it, guys. But the B2H6 is nothing but the dimerized form of BH3. But it's not a normal dimer. It's not a dimer which is forming a coordinate covalent bond, because hydrogen is not an electronically weak species to make a coordinate covalent bond. Then what kind of bond is hydrogen making here? Because hydrogen's valency can never be two, one only. So what is this bond? Where hydrogen is acting like a bridging species and it is forming two bonds. Guys, this is our world famous banana bonding. Okay, I guess you've heard about this thing, banana bonding. Guys, banana bonding, the concept of banana bonding goes like this, that although I am drawing them as two different bonds, but it is actually one bond. So this entire thing is consisting of two electrons, like one single bond. But the only problem is, in between one natural bond, there are two electrons, but two centers. This is one center, this is another center. So general bonds are going to be called as two center, two electrons. But here they say that it is also one bond only, not two bonds. Hydrogen, it's just the centers are three. So they call this kind of bonds as three center two electron bonding. There's often asked this question, B2H6, how many 3C2E bonding are there? You're going to answer that there are two 3C2E bonding. People say four. Are why four? Are these two different bonds? No, no. This is one bond only. So there are two 3C2E bonds are there. How many 2C2E bonds are there? When two center two electron normal ones, these are four hydrogen bonds. This is a very, very important topic about this structure of B2H6. Okay, now that is all about this chapter, guys. All the important questions have been covered up in here. You can now go through the NCERT once, read it through once, and then, guys, you can start solving the questions of the PYQs and everywhere. Yeah, there are a lot of equations in here. Definitely go through them. Definitely try to remember them. Otherwise, you are not supposed to fall into trouble with the conceptual question, guys. Every single conceptual things have been covered up. So you just use those things and you'll be able to answer every single question up to JEE Advanced level. There'll be no issues with it. Okay, guys. So let's keep it up to this for this video. I'm gonna watch you again in the second video, where, guys, we're gonna talk about group 14. And now the best part of this video, if you have watched it till the end from the beginning, the best thing is, guys, I have taught you the concepts of more or less the entire P block. All right, in a way I have taught you this. If I just consider the small things out, I've taught you all the concepts together in this one video only. So all the next videos would not be this big. There'll be small videos. Like group 14 probably would be done in 30 minutes or something like that. Okay. So now you make sure, guys, you watch the entire playlist, the entire series. Subscribe to the askIITians channel, because I'll be keep on posting more and more videos of of the P block in here. This would be super duper important for your JEE preparation here, because it is not in the NCERT anymore. So the teacher's note, the class note is something that is all that you're going to be referring to. And if you really want to study from the NCERT, guys, the past NCERT pictures are there in the Google as well. You can download it from there and you can read the chapters from there as well. Okay. And otherwise, my notes are more than enough for you as well. If you really want to follow a book, guys, the best book for inorganic chemistry would be JDD, that you can buy and you can refer to that book as well. And there also, you're not going to see anything new other than whatever I taught you. Yeah, these top concepts can be asked again and again